Hello everyone and welcome to our presentation today. Let's start first by introducing my team, Mira, Nada, Passant, Mariam, John, Anas, and myself, Ahmed. First, I need to note that my project is under the supervision of Dr. Cherif Salama, who is engineer Ahmed Moro from Siemens. Okay, let's start by imagining that we have a Mercedes. We all know that Mercedes is an amazing car with a lot of smart features, but have you ever wondered how all of these features work together seamlessly? Think of a Mercedes like a big complex orchestra. In orchestra, different musicians play different instruments, but they all need to coordinate to create beautiful music. Similarly, a Mercedes has many parts or components, like the engine, brakes, navigation system, and so on. Each component has its own job, but they all need to work together to make the car run smoothly. And this is exactly where a system called AUTOSAR comes in. AUTOSAR provides a set of rules and a common language that all components need to use to communicate with each other. By this way, the engine will know when to start, the brakes will know when to stop, and the navigation system will know how to give you directions without any conflicts. Okay, now let's imagine that we have engineer Iman, which owns at a Mercedes. Iman wants to customize the behavior of some of the car electronic control units or ECUs. In order to do this, she needs to configure certain modules in what's called ARXML files. These ARXML files will then be deployed to the car ECUs and will define and describe the modules and their interfaces according to AUTOSAR standards. But the question is, how do we write these RXML files? Unfortunately, Sarah will be suffering because writing RXML files manually is a nightmare. These files contain thousands of lines of code with endless and repetitive sections. She would have to navigate through complex. She would have to navigate through thousands of code to make every single line is correct because one small mistake will have the entire system to fail. The good news is that Sarah could use some configurators to help her, but it's also time consuming with a huge number of clicks, and it also comes with a steep learning curve. She would have to navigate through complex menus and settings, and it also can take more times to get everything just right. And from this point, we are here with our project Automoto to save the day of Sarah and other engineers. Automoto takes normal English description from engineers to describe their desired RXML components, modules, and parameters, and so on. Then our AI model will process this input, and just like that, the RXML file will automatically generate it. From this point, can you imagine how much time is saved from only this feature? You will only need few seconds instead of taking several hours just writing your RXML files or even using configurators. Our work doesn't end here. Our RXML files will go into our configurator, which can edit parameter values, validate constraints, and regenerate RXML files again. The next feature is to validate RXML files against AUTOSAR schema. After that, finally generating C and H files that can be deployed to the car ECUs. And now, Iman can complete her task so easily. Perfect. All of these features are seamlessly integrated into our tool Automoto, which my colleagues will introduce in details, revealing how this magic happens. Thank you.
So, in order to start building our tool, we needed first to start picking an AUTOSAR module to start building our data set and generating a data set to train our AI model on. So the first step was to choose the AUTOSAR module. And honestly, that's how we were at the beginning of the selection process, lost among several complex functionalities of AUTOSAR modules and tens of them. So we had to narrow down our thoughts into this selection criteria to choose the most suitable AUTOSAR module, which is based on the number of configuration parameters, the complexity of module functionalities, the dependency to other modules, and the hardware dependency. That's why we started doing a survey of all AUTOSAR modules that were around 80 modules, gathering their functionalities, characteristics, and comparing among them and filtering out the most suitable modules. So we decided at the end to proceed with CAN Network Manager, which is an AUTOSAR module that manages the communication over the CAN bus control area network among the different ECUs, electric control units in the car. And it's managing the data transmission and synchronize messages among these components. And that was the first step of our solution. And now we will go over the overall design.
So now I'm gonna present the technical details of our solution for you. Automoto is the integration of three main parts: AI model, configurator, and generator. Starting with the most important and innovative part in our project, the AI model. Here comes the first obstacle. We couldn't find the fuel of the AI model, which is the dataset. Since AI hasn't been applied in this field before, we couldn't find a dataset of ARXML and their corresponding English descriptions. We couldn't even find a dataset of just ARXML files. So we had to create our own. We intuitively started by writing Python codes to generate a dataset of ARXML and their corresponding English descriptions. But when we started training the AI models on these datasets, we found that the ARXML files are too lengthy, so the training is a very, very time-consuming process. So we had to look for an alternative for the ARXML. And we choose YAML. YAML is a serialization language used in configuration files. And we decided to train the AI model on generating them and then deterministically converting YAML into ARXML using Python codes. And the next question that should come to your mind is, how did YAML contribute to solving this problem? As you can see, this is a very short and simple snippet of YAML from our dataset. It has a CAN global config container, and it contains 32 CAN channel config containers. Each of them has 147 instances of CAN RXBDU. So, in the corresponding ARXML, there is 32 times 147, which is more than 4,000 instances of CAN RXBDU. Each of them take around 4 lines to be written, so the length of the corresponding ARXML is more than 18,000 lines. So now you can imagine the difference and how this tweak increase the number of tokens needed for training. And here you can have a look on the final format of our dataset. It's English description and YAML concatenated together in JSON format, ready to be injected to the AI model. And regarding our contribution to the community, we generated 12,000 rows of training dataset. We did that by parsing the basic software module definition and imagining different scenarios of different containers with different multiplicities and all the parameters with a wide range of values, along with 1,200 rows of testing data set, and both are publicly available in Hugging Face. And now I leave the floor for my colleague Anas to explain our work in the AI model itself.
Thank you, Mariam. Okay, we have the data set. What's next? That's right, model. So training a model from scratch is a very tedious process. It's going to be a very hard process and time-consuming and not practical for the current usage. So we set out to try to find a model and fine-tune it on our data set. So what do we need from our model? The first thing is that we needed to have an accessible API. So we needed to import it in our code in order for us to integrate it in our application. The next thing is that it has to be a very smooth fine-tuning. It has to be very flexible for us to fine-tune it in our dataset. And the last thing is, of course, it has to be accurate with very few hallucinations. So we set out for an adventure to find a model. The first thing that we looked at is code lemma. And we've squeezed the best out of the model. We tried varying many parameters. And then we tried another model that was lemma 2. Of course, the models that are out there with accessible API are very few. So the one we found is the lemma 2. And we did the same thing with it. We squeezed the best out of the model. And then we tried training in our data set. So what we found is that code lemma has a very high structured programming. So it's very suited for programming needs, but it's very low in lingual understanding. So it has very low understanding of various English descriptions, and that makes it a little bit hard to generate enough good output. But lemma 2 has moderately structured programming, which is just suited to our needs, but very high lingual understanding because it's a language model in the original time. It's not a coding model, it's a language model, but it does generate good code. And it's worth mentioning that code lemma, due to its low lingual understanding, did generate some garbage at the end of the file. But lemma 2, we were able to use its versatility in language in order to have a code-generated English dataset, yet able to produce correct output with various English descriptions. So at the end, lemma 2 is the winner. And so we fine-tuned the lemma 2 model on our dataset. And then we integrated in our model. So this is a screen in our application. So this is a screenshot of how it looks like. We enter the English description, and then this generates the file ARXML successfully.
And now let's talk about the configurator. So what do you think is important in Sarah's configurator GUI? First of all, we have basic software module definition parsing. And here you can see that it contains description for containers and parameters. And it contains lower and upper multiplicity for these containers. And what we mean by lower multiplicity is the minimum number of instances you can create from that specific container or that specific parameter. And also, Sarah has module ARXML parsing, and here it is different from the basic software module definition in that it contains values for the parameters, and it contains specific configurations for the containers. Then we have also ARXML extraction, and here in the GUI, you can edit values in the GUI, and after you finish editing, you can re-extract the ARXML file again. But how is Sarah going to check that the validator is doing its right function and it's working as she wants? First, we have validating the parameter value validation. So you can enter value in the GUI, and after you finish editing, we go and check that again is the basic software module definition. And if it is wrong, we display that a wrong error as follows. Like here, oops, something went wrong in container canon m channel config. The parameter canon m node ID is out of range. We also have ARXML parameter and configurator multiplicity. So we check that the parameter and configurator multiplicity and the container multiplicity, we validate that again is the basic software module definition. And if something went wrong, like here, canon m function period parameter is not found, so we display an error as well. We also have validation for ARXML hierarchical tree. So we validate that the tags are displayed correctly under each other. For example, here, we validate the parameter tags is under the container tag and not vice versa. We have also validation for the tagged hierarchy. So we check that I am under my correct parent. So for example, in our module, Canon M Network Manager, I am validating that Canon M channel config is under Canon M global config and not vice versa. And here's our generalized tool. So our tool is generalized not only for CAN Network Manager, we also tried using it for other modules, like here as shown, we use it for COM module. You can, it parses the ARXML file, you can edit in the ARXML, and also you can extract the ARXML file again. And finally, here's the integrated version for Sayers UI. You have the AI model, and you can extract the ARXML, edit it, and generate the CNH files to be ready for extraction. And now we are going to continue with a generator.
Now we have our configurations validated, but now we still need the C code corresponding of these configurations. That's how our generator is working. The generator is responsible for generating static and dynamic code. And here what I mean by static code is that it's fixed functionalities of our chosen AUTOSAR module, that's the CAN Network Manager. And these functionalities are implemented and generated with all configurations. And basically, it is transmitting, getting the status of data, synchronize messages over the campus, and disable or enable the communication. And these functionalities are referred from the software specifications of CAN Network Manager published by AUTOSAR standard. And we refer to them to implement our functionalities. And the other generated code is a dynamic code, and it is dynamic because it's based on the configurations of the users that are generated from the configurator. And we are doing here a conversion from the ARXML configurations into C code. And this is done by a Python script that preserves the containers and parameters hierarchy tags and converts them to C struct objects for the functions to be called on. And now we have our C code ready to be deployed on CAN Network Manager. Now it's the time for the testing part.
Now to the moment of truth, we need to test each part of our project to make sure that everything is working perfectly. The first part of testing involved testing the AI model. The AI model takes as an input the English description and outputs the YAML. It was originally tested on 1,200 samples, and they all outputted an accuracy of 100%. This was worrying at first, but then after talking with our supervisors, we reached the conclusion that since it was trained on 12,000 samples, this is an expected output. Also, we tested this model on 10 manual models that we made, 10 manual samples that we made ourselves, and also output the correct output perfectly. The second step of testing is testing the YAML to make sure that it outputs the ARXML file perfectly. This step was tested using also 10 samples, and this is due to the fact that it's a deterministic process, so it doesn't need much testing. The third step of testing was making sure that the ARXML file follows the basic software model definition. This was done by the validator that Nada already talked about. The final step of testing was testing the generator itself. The generator itself was tested using unit functions. It has two types of functions. Functions that depend on other modules and functions that don't depend on other modules. The functions that depend on other modules were tested using mock testing, while the functions that don't depend on other modules were testing using assertion. This is due to the fact that mock testing basically means making a mock object that represents the other modules so that we can mock the behavior of the function that we created.
So our main mission is the community deployment of AUTOSAR projects using a user-friendly configurator tool that is enhanced with AI capabilities. Additionally, we are writing a research paper to discuss our findings and our progress so far. So let's go through the outcomes of our project that support our goals. Now, I'll be presenting a demo for our software tool. So this is the interface of our tool. And we have here two main tabs, basic software module definition tab and ARXML reader tab. For the first tab, it shows the containers and sub-containers of the basic software module definition with some info about each parameter in it, like the description, the default values, and the range. For the second tab, which is the ARXML reader, it shows also the containers and sub-containers, but for the uploaded ARXML. And the difference here is that we can do some changes on it to extract a new ARXML. And these changes can be done through a Dropbox or a text box like that. And some validation is done as Nada discussed before. So now let's go through the whole cycle, starting with the AI converter. We begin by inserting the English text prompt for the desired ARXML. And here we need to create a CanNM module with a global config container that contains 4 CanNM channel config and includes a specific parameter to be true and 13 RxPDU containers with a specific ID as shown here. So now the AI is generating this ARXML directly, automatic. And we can see here that it's got generated in this directory. And now we can upload it again in our tool to do some changes on it or continue our cycle directly. So after the upload, we can see here that the tool got updated automatic. So here we can see the 4 containers with the specific parameters that we changed and the specific ID that we did input. So now we can extract the new ARXML after the additions. And we can see here that it's got generated under the name output.arxml. And now we are ready to the final step, which is generating the COH files. And here is the generated file, and we can also make sure from the output the specific IDs that we did input and the specific parameters that we made to be true. So this was our first output, and we made our project resources publicly available on GitHub to encourage collaboration and innovation with the interested community. And the second output, which is a research paper, we are started to draft our our first version from the paper that discuss our findings and our progress so far. In preparation to apply for this conference, IEEE conference, and we are aiming to submit our paper under track 4 AI applications for industry, and this conference is due the 27th of May. And there you have it. This was summarizing our efforts during the last year, and we are looking for your questions, and thank you all for listening.